Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over a couple of practice problems where you are going to determine the pH of a salt that contains an anion that is acting as a base. So the first one we have is 0.100 molar solution of sodium with the formic acid. This is the conjugate base of the acid, formic acid, which is a weak acid. Therefore, this is going to be a weak base. So this anion is acting as a weak base. So we're going to figure out the pH of this solution. So the first thing you want to do is write out your equation, and you're going to have also your ice chart. So you're going to do your ice chart. So right away, you have CHO. So this is going to be CHO2 minus aqueous plus you have water, H2O liquid, and that's going to go to, so this is going to take a hydrogen from water, so you're going to have HCHO2 aqueous plus OH minus aqueous. So it's all a 1-to-1 ratio. We're going to set up our ice chart. So the initial concentration from the beginning is going to be for this anion, it's going to be 0.1000 molar because the ratio of the whole to the part is 1-to-1. So the molarity for this is going to be the same for this ion here. And then we're starting with 0 concentration here, and practically 0 here. There is some hydroxide ion concentration from the autoionization of water, but it's so small that we can ignore it. Okay, so this is the initial concentrations. Our change, since we have 0 over here, Le Chatelier's principle says it's going to move in that direction. So we're going to lose some of our reactant here, our base, and we're going to gain that amount in terms of these two, in terms of X. So because of the 1-to-1 ratio, we have X to X to X. Now, to get the equilibrium, we add these together. So the equilibrium concentrations is going to be 0.100. We'll get rid of them. We don't need the molarity. Minus X, and this will be plus X, and then plus X. Okay. So now that we have our equilibrium expressions for the concentrations, now we need our Kb expression. So we need to find what the Kb of this anion is. We know it's the anion of a weak acid, so we could look up the Ka value for formic acid. And then what we can do is we can use this equation. Remember, the Ka times the Kb is equal to W, which is 1.0 times 10 to the negative 14. So we look up Ka and we solve this equation for Kb. So the Ka value is, let's see, the Ka value for formic acid is 1.8 times 10 to the negative 4. So 1.8. So the Ka value is 1.8 times 10 to the negative 4. So we divide both sides by Ka. And so Kb, so then Kb is equal to 5.6 times 10 to the 11. 5.6 times 10 to the negative 11. And that's equal to the expression of this equation. So it's going to be the concentrations of the products over the concentration of the reactant here, the So it's going to be OH minus concentration times the concentration of HCHO2 over the concentration of CHO2 minus. And so now we set this, we substitute these expressions in. So these two multiplied is going to be x squared. So 5.6 times 10 to the negative 11 is going to be equal to x squared over this expression here, 0.100 minus x. And now we can go do our x is too small approximation. So we can do that, and then we'll have to test it later to see if it's valid. If we look at the KB value here, negative 11, and then we look at this, this is 1.00 times 10 to the negative 1. That's a difference of like 10 to the 10. So that's a huge difference. So it's probably going to be really valid. So we get rid of the x here, and then we solve for x here. So we multiply both sides by 0.1. We take the square root of both sides and we get x. So in that case, x ends up being equal to 2.4 times 10 to the negative 6. So 2.4 times 10 to the negative 6. And again, if you take x, so 2.4 times 10 to the negative 6 divided by the original concentration, 0.100, multiply that by 100, you get a percentage of 0.0024. 0.0024%. So this is much, much less than 5%. So it's a valid approximation. So the x is too small approximation is validated. So x is what? X is the amount of hydroxide ion. So at this point, what we do is we have to find the pH. So we need the we need the hydronium ion concentration. So remembering that H3O plus concentration times the hydroxide ion concentration is equal to Kw, which is equal to 1.0 times 10 to the negative 14. Now we can plug this into our hydroxide ion concentration. So then H3O plus times 2.4 times 10 to the negative 6 is equal to 1.0 times 10 to the negative 14. Divide both sides by 2.4 times 10 to the negative 6, and you'll get your H plus concentration. And we find that to be 4.2 times 10 to the negative 9. So the concentration of hydronium ion is 4.2 times 10 to the negative 9. Is that right? Is that what I said? 4.2 times 10 to the negative 9. Yes, molar. So then all you need to do now is take the negative log of this value. And so when you take the negative log of this value, you get 8.38. So the pH is equal to the negative log of this number here, 4.2 times 10 to the negative 9 molar, and that gives you a pH of 8.38. 8.38. And again, for sig figs and decimal places, remember the rule is if you take the log of a number, the number of sig figs you have in the number that you're taking the log of translates into that number of decimal places that you need in your pH, or in the answer that you get, in this case pH. So I have 2 sig figs here. That means I need 2 decimal places in my answer, and I have it right here. So 8.38, that's the answer. So that's the first problem. And then I'm going to do the second problem. Okay, so for the second part, so this time we have 0.250 molar of the sodium acetate, and we're going to figure out what the pH of this one is going to be. So in the same way, we have our balanced equation, and you're going to do your initial concentration. So we have 0.250 here, and we're going to have 0 here and practically 0 there. And then because we're going to go in this direction, it's going to be minus x here, plus x for the change, because it's a 1-to-1 ratio for everything. And then we add each of these together, and we get 0.250 minus x, and we get plus x. And now we have to do the same thing here. So again, because Ka plus multiplied by Kb gives you Kw, we need to figure out the Kb for the acetic acid. So the Ka for acetic acid is, the Ka value for acetic acid? The Ka value for acetic acid is, it's going to be 1.8 times 10 to the negative 5. So Ka value is 1.8 times 10 to the negative 5. Okay, so here we're going to use this equation here again. So that means that 1.8 times 10 to the negative 5 multiplied by Kb is going to be equal to 1.0 times 10 to the negative 14. And then we just solve for Kb. So if we write Kb down here, Kb then is going to be equal to, it's going to be equal to 5.556. So 5.56 times 10 to the negative 10. And again, this is going to be equal to the concentration of OH minus times the concentration of this part here, HC2H3O2, all over the concentration of our acetate ion, which is C2H3O2 minus. And then we're going to take our equilibrium expression, so 5.56 times 10 to the negative 10 is equal to, it's going to be x squared over 0.250 minus x. And then we can do the x is too small approximation, so we'll get rid of x. Multiply both sides by 0.250, square root each side, and then you get x is equal to 1.178 times 10 to the negative 5. And so that x value is your OH value. And you'll find that this is validated because if you look at the size of the Kb here, it's a very large difference. And from here you would find the H concentration